Assalamu alaikum wa rahmatullah. Hello guys, today we will talk about backpropagation and other differentiation algorithms in our book chapter 6. Let's get started. So in previous sections we talked about forward propagation, so that information comes from the x, it goes to the cost function. And now we use backpropagation to do the backprop. So information goes from x to first layer, second layer, third layer, and to the output layer, and then we calculate the cost, right? And now we need to go from this cost backward to the first layer to update the weights and biases. So backpropagation is simply uses chain rule and differentiation algorithm, and one of the differentiation algorithm to find these gradients by going the backward. And main advantage of backpropagation is that it is using dynamic programming. So in order to understand well, let's represent the neural network as computational graph. Assume if we have this kind of, so this is one example of computational graphs. So here, for example, we have x input and we have weights, and we get multiplication, and we will receive resulting metrics, and then we will add this resulting metrics with this b bias, and then we will get another one, and then we apply a ReLU function. So this is typical neural networks, how it works in graphical representation. So in terms of backpropagation, so now I explained the path of forward propagation. So now from h we will go backward to the x to update x and to update the weight, and that process is called as backpropagation. And using these computational graphs, this kind of representation is easy to implement also. So if we want to find the gradient of z given the x value, we find the gradient between them. If we have y, we will find derivative of z given by y, and then derivative of y given by x. And that is simply what this chain rule stands for. So assume we have this kind of network. So we have weights, and we apply a function and we receive x, and then we apply a function and we receive y, and we apply another function, we receive z. And if we want to find the gradient of z with respect to weight, we need to find the gradient between. So we need to calculate each one. So we will go back. Very simple. And this is the implementation. So here, if you pay really carefully attention, so if we want to find the gradient of z with respect to weight, we need to find the gradient of z with respect to y, and then y with respect to x, and x2 with respect to w. And here you can see that we need to find the prime of y, and then prime of x, and prime of weight of w. And then the prime of y is, what is that? So if we go to y is equal to what? The function, the f function, and so function and applied to weight, and function of weight, and function of weight. So you can see when we do backpropagation, we are calculating again here, right? We are calculating again. But indeed, actually, when we do backpropagation in frameworks like in TensorFlow, in PyTorch, and basically they are used to not calculate these things twice. So backpropagation is that we calculate everything by going forward, and when we will go back, we will use calculated things. And in order to use these calculated things, we apply dynamic programming, and in dynamic programming we applying table filling algorithm to not calculate the same thing twice. But there is always trade-off between the memory and the speed. So if we don't calculate If we calculate only once and store every calculation in the memory, it will be slow. If we use some kind of delta value to calculate and store some certain calculations, then it might be efficient. So basically, so backpropagation calculates the gradient and going from top to first layer, and without calculating twice, trying to not calculate twice to be efficient. And now there is a algorithm explanation of them basically, and let's go to the implementation. So let's say if we apply backpropagation to the fully connected multi-layer perceptron. This is feed-forward network, and if we apply it here, then let's look to the graph. Now let's go here. So let's look to the example. So let's apply backpropagation to the multi-layer perceptron. So assume we have a cost function of the network, and plus we have some regularization. And if we represent this model as graph, so we can see in such way, so that we receive this x and we have this weight. So we go this way, this direction, and we calculate the cross entropy as a cost. But we also go another direction to calculate the regularization, and we get the summation of this cross entropy and this U8 to get the final cost function. And now what we should do is that we should update the weights, right? We should update the weight 2 and weight 1. So in order to update weight 1, weight 2, we can go this direction, which is a bit complicated, or we can go this direction. And it explains how it goes that way, and it goes in one way or another way, and one of them is easy, another is a bit difficult. And currently frameworks like PyTorch, TensorFlow, they care too much about this backpropagation, and they apply it, and they care about other things like data flow of data type and about numerical imbalance if there exists, or some kind of problem with numerical computation. And this frameworks cares about that backpropagation implementation. But now what we saw is that it is naive explanation, naive implementation also of overall how the backpropagation is working. And indeed, backpropagation is only one of way of calculating the gradient. And as in books, as authors are saying that there are other different kind of methods, algorithms to calculate the gradient, but still this backpropagation way is popular among the practitioners, and yeah, it's doing good. But still there might be new ways of calculating the gradient. That's about backpropagation in simply, and let's talk about historical notes. So in historical notes, let me talk that the chain rule was invented in 19th century. The chain rule was invented in 17th century. The calculus, algebra was a long time, but the gradient descent was invented in 19th century, right? And what happened is that we started in 1940s, in 1950s with linear models, and then we faced it with a problem of XOR, so that the linear models cannot learn even simple models, even simple problems. And then we went from that problem, And we solved that problem by using activation function, by using the feed-forward networks. And then we faced another problem, and then we invented backpropagation, and we applied backpropagation into practice, into the languages, into the programming languages. And then in 1990s, the research boomed again in computation, in machine learning, and from that time the research was booming, but it didn't give enough efficiency, enough results. And in 2006 again there was a renaissance in deep learning, and that these feed-forward networks start to do a good job, and we understood it is power. And from 2012 approximately, these feed-forward networks are well understood, kind of, and they used a lot in academia and in practice. And they are also used for they also used to create probabilistic models such as variational autoencoder, generative adversarial networks, and etc. And I want to tell about that by giving right dataset, by giving right cost function and optimization, we can have good feed-forward network models. And that is also, I want to tell you about rectified linear units. In 2000s, rectified linear units were weren't recommended to use, but actually they were. In 2006, the scientists figure out that these rectified linear units are indeed one of the good factors for improving the performance of models. And then from that time, these rectified linear units regained popularity, and they become one of the important and popular unit activation function in deep learning. And that's all about chapter 6, guys. I know there is no practice yet, but I will try to do video for the for multilayer perceptron. Stay tuned. And then this is about these basics of MLP, multilayer perceptron. And this is indeed very good. Please read this chapter, or you watch other YouTube videos by the authors, and it's really great, really great. And if you have questions, write in comments. See you in next videos. Bye bye.